Welcome, ladies and gentlemen, to another exciting episode of Dave Does Maths from Home. Today's episode is about section 6.2. We are talking about areas between curves. We left off with we started off section 5.5 with me saying that I wanted to do fun, interesting, exciting things with integrals, but that before we started to do fun, interesting, exciting things, we needed to step back and do a lot of technical how-to things, so that we could handle the complex, the weird, the exciting integrals. And now that we have done a simple version of that, we are going to pause the integration techniques for a bit so that we can do some really cool stuff with integration applications. And then once we finish cool stuff with integration applications, we're going to come back to integration techniques and learn to do even more weird stuff. We're kind of going to back and forth a little bit. So this is our first Calc 2 sort of interesting integral application event. And hopefully we remember from the most of chapter 5 that a definite integral will give you the area beneath a curve. And beneath is sort of the standard word for this thing. Beneath is sort of, it's not the best word for it, because sometimes if you have a curve that looks like this, you're not getting the area beneath this curve. You're getting the area between the curve and the axis. So it's not this, it's this, which in this case is above the curve. We sort of just assume that most curves are positive, and we say beneath the curve. What we really mean is between the curve and the axis. That's really what the definite integral is giving us in terms of area. So today we're going to do something slightly different. Instead of finding the area beneath a curve, or between the curve and an axis, we're going to find the area between two curves. So we're going to dive directly into an example of this so we can see what it looks like. I'm going to start out with my favorite example. This is the graph of y equals x squared in the first quadrant. This is the graph of y equals the square root of x in the first quadrant, and I want to know how much area is in here. That's the goal. We're going to find the area of this weird crooked eye-shaped thing. And here's how we're going to do it. We're going to start by finding the area beneath, for now I'm going to say from A to B. We'll figure out what the actual bounds are in a bit. But for now we're going to find the area beneath the top function. The top function here is square root of x. So if I do the area from A to B of square root of x, it's going to give me this. All the way from that top function down to the axis. Actually, let me do this. That's what I'm drawing in red. I'm going to write these in red. We have the technology to color code this. So that's the integral from A to B, whatever A and B are. That's the integral of A to B square root x dx. This is the top function. We're also going to find the integral from A to B of the bottom function. The bottom function here is x squared dx. And if I find this area, it'll give me all of this in green. So if I do all of the red and then subtract all of the green from that, I will get this black shape that I actually want. So this black shape's area is the integral from A to B square root x dx minus the integral from A to B x squared dx. So this is the general theory of what's happening in this section. Generally speaking, you can always find the area between two curves by subtracting the areas beneath each of them. You figure out which one is on top, you calculate that area. You figure out which one is on bottom, you calculate that area. You subtract those two areas and you get the area in between the curves. Here's where things are going to get just a little bit more interesting. We remember from our discussion of how integrals work and integral properties that subtraction is safe. So here's a step that we can do to save a little time. I don't have to do this as two separate integrals. Because subtraction is safe, I can do one integral of the top minus the bottom. So you can think of this as finding the area under the top, finding the area at the bottom, and subtracting the two to get the area in between. That's one way to think about that, and that is a perfectly acceptable way to think about that. The other sort of way to think about this is if you look at the difference between the two functions. That's like, I'm going to make a second drawing down here so I can draw on it. When we do these integrals, the actual analytical math that we do involves antiderivatives, evaluating the antiderivatives, and that's how we get the area. But the idea that these integrals came from is Riemann sums. They came from the idea of slicing this thing into little rectangles and adding up all the rectangles. So if you do these two integrals separately, that means you're taking rectangles that look like this, and then you're taking rectangles that look like this, and you're subtracting those two things to get the amount of space in between. And that is a perfectly acceptable way to think about that, and you can simplify those steps by combining those two integrals. But there's a different way we could think about this. We could think about this. The difference between those two things is like taking a rectangle that's this tall. The height of this rectangle is the top minus the bottom. So in our case, that's root x minus x squared. So you could use this entire expression, root x minus x squared, as the height of a rectangle that does not connect with the base here, and then you can just find the area that way using a single integral, and this is the geometric interpretation of what's happening in this single integral event. And of course the width here is dx. The idea of this integral is you're taking so many rectangles, infinitely many rectangles, and so the width of them is getting infinitely small. And that infinitely small width is always just dx if it's an infinitely small chunk of the x-axis. That is what dx means in this context. That'll become really important later. So this is all the theory and background behind what we're doing here. So let's actually just do it. Oh, wait, before we actually just do it, we need to know what A and B are. I've been using A and B so that I can just talk about the theory of this without having to get into the actual specifics, but it's time to get into actual specifics. We need to know what are the x values that define this region. And to get that, the two x values that define this are going to be the points of intersection between these two functions. And so you find points of intersection by setting the two functions equal to each other and solving it for x. In this case, we have to solve this equation by squaring everything, so we'll get x to the fourth equals x. And we can subtract x from both sides. Get x to the fourth minus x equals 0. And this is a polynomial we can factor. It factors into x times x cubed minus 1. And so our zeros are 0 and 1. So So this point is x equals 0. That's our A. This point is x equals 1. That's our B. So we now have all of the tools that we need to find the area between these two functions. I'm going to erase most of this and start over at the top with lots of room. Sorry. So we have the integral from 0 to 1 square root x minus x squared dx. In a way, when you do these problems, or one way to think about how you're doing these problems is to think of like the four different sort of bounds. You need a top and a bottom to go inside the integral as your top function and your bottom function, and you need a left and a right bound so that you know how far you're going in each direction. So top, bottom, left, right, it all comes together in one integral, and this integral is the integral of root x, that's x to the 1/2, and that is, I don't need the integral sign anymore, 2/3 x to the 3/2 minus 1/3 x cubed, evaluated from 0 to 1. So this is 2/3 of 1 to the 3/2 minus 1/3 1 cubed minus 2/3 of 0 to the 3/2 minus 1/3 0 cubed. So this is 2/3 of 1 minus 1/3 of 1 should just be 1/3. And this is 0. So this area between root x and x squared is exactly 1/3. One of the reasons I really like this problem is because it illustrates that these two functions perfectly split this box into 3 parts. This is the x equals 1, y equals 1 box. This box has exactly 1 square unit of area, and this is 1/3, and this is 1/3, and this is 1/3. These two functions perfectly split this into 3 equal sized pieces. And I think that's really cool. I have a lot more to say about areas between functions. I'm going to cut this video right here so that we can leave on this incredibly positive note that this is really cool. I'll be back with another video right after this.